All right. Question. How do you do the product rule? How do you do the product rule? All right. Second, I'll focus my dum-dum people. Shh, don't be a dum-dum. So, second D first. The flavor is what it is. Calm down. Notes open. Okay, Katrina, when I say second D first, what do I mean?
The second thing times the derivative of the first thing.
Good. Second thing, which is ln of 5x plus 1, times derivative of x squared, which everybody is 2x. But I'm not done. Plus. First of all, why do we have to use the product rule again?
Because it multiplies.
X squared times ln of. This isn't product rule, but this is. Plus, first, rewrite it. Uh-oh. Why did I say that we need a chain rule? D second. It's an ln of x or an ln of u? ln of x or ln of u? Why? It's something more than just x, right? Okay, and u is an inside, and there's an inside. So, how do I take the derivative of ln of u? 1 over u times u prime. And what's u prime? 5. Because the derivative of 5x plus 1 is 5. Technically 5 plus 0. Now, how do we rewrite it to make it look pretty? Well, I'm not sure if it's pretty. But that 2x should probably come in front, right? Plus, how can I combine all that second stuff?
5x squared.
Good. The x squared is like over 1. The 5 is like over 1. So I can put 5x squared up top over 5x plus 1. Now, if they were in a really, really, really mean mood, I'm sticking it to the man. If they were in a really, really, really mean mood, they could get common denominators. But we're not going to. They could put him over 1, and they could multiply top and bottom by 5x plus 1. But that's just like if you can't make it match and you're sure you've done it all right. Yeah.
So when you're finding the derivative of ln of u, it's like 1 over x, but instead of the x, it's 1 over u.
Exactly. And that's why I showed this. Because it's the same rule. Just like the derivative of e to the u is e to the u.
And then you multiply it by the derivative of u.
Exactly. Okay. So 1 over u times u prime. Just remember. Hold on, guys. It was a great question. Is the 2x allowed to come in?
No.
Why? Who's in the ln? Just this part. If we were to do something with the 2x, what's the only legal way, according to log properties, the only legal place the 2x could go? To the power. The only legal place, if we were to make it simplified, something in front of an ln actually goes up. So that would kind of make it look awful. Bridget.
So how do you say the problem when it's like
Ooh, that's coming. We haven't seen it yet, so that's why it's like, huh? Hang in there. Angela, you need that one. Got it? Alright, the next one. Question. Do we need product rule for number 4?
No.
No, because read it. Tangent what? Times or of? Of. Tangent of ln of square root of x. There's no multiplication. There's no multiplication. So, I need to use a chain rule.
Yes.
And I have an F and a G and an H. So we could go by the formula if we wanted to do that. Or we could see if maybe we can figure this out just using inner and outer. Like, where do we start? Who's on the outside? If I was to get my matryoshkas. Tangent. What's the derivative of tangent? Secant.
squared.
Whoo, gotta keep studying. What do I do with this?
Keep it.
Keep it. Derivative of the outside, keeping the inside the same, times, ran out of room. Peel off the tangent. Who's next? ln. What's the derivative of ln of u? 1 over, yeah, you could do u prime over u, or I like doing 1 over u times u prime, especially when the u prime is something messy like it. Helps me kind of spread it out. But 1 over u times u prime. What? Oh, that's right. Peel off the x's turn. Ooh, who is that if I was to rewrite him? X to the
Negative 1/2. X to the 1/2.
1/2. And then we bring down the 1/2
So it's 1/2 squared.
and raise x to the negative 1/2. I did it fast, but we've done square root of x at least a few times, right? But remember, square root of x is to the 1/2 power. Bring down the 1/2. 1 on top, 2 on bottom. Make x to the negative 1/2, which puts them in the denominator. So if we were to simplify this whole puppy, these are not, Christian counted the other one, these are not in secant squared, so I have to put them in front. A square root times a square root is just an x, right? And then we have our nasty secant squared ln of. What is one quick hint as to whether or not you're doing the chain rule properly? Do you see times u primes? That's the question.
Is there forgetting something?
What do I forget?
It's like it's one of those like h of g of
True, but I did. That's f prime, that's h prime, that's g prime. No, I did it backwards. F prime, g prime, h prime. So I did the derivative of tangent is secant squared, the derivative ln is 1 over, and the derivative of square root of x is 1 over.
never mind.
I just did a quick ln of u rule, so I kind of did it all at once. Does that make sense?
Okay.
But I do have my 2 times multiplications for the outside, then the middle, then the inside. Yeah. All right. He was a little rough. But are we still breathing? Are we still there? Does it kind of make sense? Do you at least see the difference between product rule with a chain rule, but either way, a big product rule and just an entire chain rule? Product rule, you need a times. Chain rule is a lot of ofs. Okay? And remember, bunny rule, bunnies multiply, we multiply by u primes. Okay, Bridget, here's your question. What if we have a log with a base other than e, aka a log other than ln? Here's the dilemma. ln's rule, was he that hard, the derivative of ln? No, we have to memorize it, but the derivative ln of x is 1 over x, done. Or the derivative ln of u is 1 over u times u prime. That's why I said last year you should come to like ln and use ln, because he's a lot easier than any other law. Same thing with e. What's the derivative of e to the x? He's nice. He's easy. Any other to the x, 2 to the x, 5 to the x, 7 to the x are going to be so much worse. Still possible, just worse. And here's why. The way that we take the derivative of a log of any base is actually using ln's and saying, hey, she's alive. We say ln has a nice rule, so guess what we're going to do? Go to ln's. What? We can do that? We can take a log of any base and make it in terms of ln's? Yes, using a pre-cal formula called the change of base formula. So if ln is so nice, if his derivative is so nice, which it totally is, then how do I face a log of any other base? Yeah, that kind of rhymes. I put it in terms of ln. And so if I need to, remember what this means? What's d dx mean? Yeah. So if I need to take the derivative, think algebra. If I take the derivative of one side, what did I better do to the other side? Take the derivative. So I'm going to figure out what the derivative is of log base b of x by deriving, what do I have? Quotient rule. Kind of.
Quotient chain rule.
I actually don't need a quotient rule if we rewrite it. No. That's illegal. No deriving, just rewriting. Is there a way to rewrite ln of x over ln of b? You could do ln of b to the negative 1. I like this better though. And here's why. Who's b? Is he a variable or is he a constant? He stands for a constant. What do I mean? It'd be like log base 2 of x, or a common log base 10 of x, but the 10 wouldn't be there, or log base 7 of x, or log base... b's just a number. If I establish b to be like 2, log base 2 of x, this would be ln of 2. Is ln of 2 a number? Yeah, plug it in your calculator. It's a funny, weird decimal that no one wants to deal with. But is it a number? Yes. So why did I pull this off to the side? Because he is just a constant. And what can I do with any constant?
Grab it.
No. Constant multiple. When he's in front, when he's multiplied, I just keep him, right? Right? If I have 5x squared, the 5 stays, and you bring down the 2, right? The constant stays. So what do I do with ln of b? He stays. Times, what's the derivative of ln of x? 1 over x. So wait a minute. The derivative of log base b, any log, is it going to have a 1 over x piece? Yeah. But it's just going to have an extra piece as well, because ln of any base other than e does not simplify and needs to remain. Now, as we know, kiddos, if we were to put this together, fractions, multiply the tops, multiply the bottoms, are we going to leave the x as the later piece, or are we going to put them in front, and why? Front, because if we put them right next to ln, aren't we going to get confused? So let's go ahead and write it 1 over x ln of b. And what's going to change if, instead of just an x, I have log base b of u? It's going to be 1 over, if I have a u instead, 1 over u ln of b times u prime. Right? Any derivative rule can be made a chain rule, where it's just a simple composition of 2 functions. And this brings us up to, hey, whew, we're ready to make a forever card out of all the log stuff. Do you want me to go back? Okay, yeah, go ahead.
So I have a question, like, let's say, how do you know
Do the functions literally just have an x alone? Or is there something else, like a 5x? Or like a x squared minus 1? Or like a square root of x? If inside ln, or inside sine, or inside cosine, or inside e to that, if there's something other than just x. Does that kind of make sense? What's the derivative of ln of x? 1 over x. What's the derivative of ln of anything else besides just x? 1 over anything else, we'll call them u times u prime. And if you guys like it, you could put u prime over u. I'm just trying to show you that it follows the rule, just multiply by a u prime. Now here's a funny one. The derivative of ln of absolute value of u doesn't change anything. Because absolute value of u, ln can only have positive domains anyway. So actually, whether it's a normal u or an absolute value, the derivative remains the same. Just something to be aware of. Sorry, not nice. It doesn't change. ln is the one thing with absolute value that nothing changes. Log base b of x, we just looked at it. 1 over x ln of b. And we just mentioned, if there's a u, 1 over u ln of b times u prime. Or that might change into, you could do u prime over u ln b. But I kind of like keeping the formulas the same, just with the u, and then just always multiplying by u prime, because then it is like a system that we can always follow. Took me a little while to get to this card, but it's because there were quite a few things that we needed to get before I could make it. This is forever number, actually I don't think you need this part of it. Where are we at, 14?
13.
Did we do 13? Okay, it's supposed to be forever 13. Isn't it 13? Probably the quotient rule was forever. Chain rule was 13, right? Remember I said there were 15 cards total once we got distracted. Now guys, look, hold on. This looks like an awful card, except what's true about these three formulas basically? They're kind of the same. It's 1 over, either 1 over x or 1 over u, and when there's a u, we do tan theta. And then these two formulas are basically the same. So it's kind of just two formulas. So I want you guys to go ahead and, here we go.
Steve, are those other ones on,
Yeah, I have up through 12 done. I'll do 13, 14, 15 by lunch today. Okay, how do we use the rule for the first example? Start off easy. What do we do with 17? States, right? Okay. Times any log, ln or otherwise, always starts the same. Any log, ln or otherwise, always starts the same. 1 over. 1 over who? Well, who's in this logarithm, guys? Just x, so 1 over x. Oh, wait, but that's ln, and he's not ln. What do we add on after x? Perfect. That's it. But you have to remember, for any log, you start 1 over who? If it's ln, you're done. If it's not ln, oh, you gotta, in a sense, compensate for the base being something other than ln. Now, if you wanted to, you could memorize the change of base formula, and every time change the base and then use like a quotient rule or that funny rewrite and then take the derivative. But if you could memorize it, life will be so much easier. Number 2. Let me give you guys a second. I think there's a U. A me? No. Can you use the formula? Anytime there's a log, start with 1 over. If you get an answer, check it with people in the group and be like, hey, let's talk it out just for a second. Speaking of which, I meant to change groups this week. I need to get grades in by Wednesday. So, probably beginning of next week. Give me one more weekend. Then we'll switch it up. Alright, check answers, check answers. You don't have them for that much longer.
2 over x ln 5. 2 over x ln 5. Oh, wait.
Any logarithm. Start with 1 over. Yeah? U. Oh, but that's for ln and he's not ln. So I need my ln of v times. Why am I still going? U. Right? Now, 6x, he's not in the denominator. He would go in the numerator. So I could simplify just a little bit. Because 6x is technically over 1 if you want to write it to make sure that we're good. The 3 and the 6 now can reduce. The x and the x squared can now reduce. And the final nice simplified answer would be 2 over x ln of 5. But you had to go through the beginning process of plugging into your formula. Any log, 1 over who? 1 over u. He's not an ln, so I have to compensate. Right next to that u, ln of 5. Then I say, since there was not just an x, I need times u prime. Derivative of 3x squared is 6x. And then I rewrite. Cool? How have you guys got there before me? How have you guys got at least one step of the process? You just got a little stuck. Okay. That's most of us. There's one more. Logarithm one. Ooh, he looks fun.
Yeah.
Question. Should I use the ln of x formula or the ln of u formula? Oh yeah. Yeah, that's not just an x. Now hold on. How do you start any logarithmic? We're going to work this one together. Start any. Oh, you want to do it on your own?
Yes.
There's an easier way, so I'm not going to actually have you go this whole way. Question. How would, pause, let's keep it basic. How would we take the derivative of any log? Start with 1 over. Okay? 1 over who? 1 over u. That's the easy part. Times. Times who? Times u. I'm just going to write this because I don't think I'm going to be able to do this in my head all at once. So I'm going to say times u prime. Does this work for signifying u prime?
Yes.
Yes, because I'm just saying take the derivative of him. And some of you were like, oh, product rule. And you're totally right. Because we would have to do first and second. Although, I'm not so sure I do first and second, though, until you rewrote it. Right?
Right.
Because don't get tricked by the trig notation. How can we rewrite sine cubed? Sine 2x cubed. What's a slave for who? I'm so confused. That would be better. Now, is this impossible? No. Is it going to be a long process?
Yes.
Yes. And to be honest, guys, if this was a problem and it didn't have ln, you would be stuck doing the long process. It is what it is. But I just said if you didn't have what? If you didn't have ln. Now, I'm not finishing this problem. I haven't done that derivative. But I'm going to take a quick time out and be like, but we do have an ln. Does that make a difference? Yes. Because ln is very unique. Actually, all logarithms are very unique in a sense that there are these properties that say if there is multiplication in the argument or powers in the argument, we can split up logarithms in separate pieces. Remember? Go look at the beginning of your notes real quick. We wrote about log properties, right? Before derivatives. ln of a times b is ln a plus ln b. Oh, maybe if I can split this up, I have lots of easier derivatives all being added together. That's actually called something. It's called logarithmic differentiation. Differentiation, taking a derivative. Logarithmic, it only works with logs. Any logs. We'll come back to this example and we'll do him a totally different way. Now, just for a heads up though, the way that we were doing it would work. The way that we were doing it would work. It's just maybe not as fun as using log properties to simplify or rewrite before deriving. If we have a logarithm, we can simplify or rewrite before deriving. Let me show you what I mean. Logarithm differentiation. Just a snazzy way of saying you can use log properties to rewrite before you ever have to derive. So rewriting, I'm not deriving it. We just saw a second ago there's a product in there, right? And isn't there a property for product? And we saw that sine cubed of 2x can be rewritten sine of 2x cubed. Wait a minute. Can't we keep going? Isn't there another multiplication? So couldn't I rewrite again? ln of 3 plus ln of x squared plus ln of sine 2x cubed, totally legal. I'm just using those properties. And anytime there's multiplication, I can make it addition of two separate ln's. Anytime there's multiplication, I can make it addition of two separate ln's. And anytime there's an argument to a power, I can put it in front. And why is that good for deriving? Hey, it's ln of x. He's super easy to take a derivative of. The chain rule's gone. Awesome. Maybe not the entire chain rule is gone. I think one of the hardest parts of this chain rule on the last one is gone as well. Have I taken any derivatives? No. The only thing I've done is use log properties to do what? Simplify, to rewrite. No derivative has been taken. Is there any way to break this down anymore? I don't think so. It's time to derive. Oh no, this is going to be awful. What's the derivative of ln of 3? 0, because ln of 3 is a constant number. No. So 0 plus, I'm just showing so that you guys know I took the derivative. Derivative of any constant is 0. Plus the 2 just chills, right? Times derivative of ln of x. Plus the 3 just hangs out. Derivative of ln of u. 1 over u times, okay, we still have a little bit of chain stuff, right? Peel off the ln. Who's next? Sine. Whose sine's derivative? Cosine. Rewrite. Times, peel off the ln, got 1. Peel off the sine, got 1. Now what? That looks messy. But theoretically, that was a lot easier than what we thought we were going to have to do on the page before. Because now we have 2 over x plus, well, 3 times 2 would be 6 cosine of 2x over sine of 2x. And if you guys want to be really snazzy and think like an AP person, you'll be like, cosine over sine, isn't that? Oh. But that's just if you want to think like an AP person who might be writing the questions and the multiple choice answers that you'll be facing. So what did I do again to break this down first before deriving? Just use log properties or log rules. Then now kiddos, we worked really hard on logarithms. We still have 10 minutes. There's one thing we haven't worked really hard on yet. And it's the last thing of this chapter and the last thing of this section. That's an example, but we might come back to him. Exponentials. Exponentials. We worked real hard on logarithms. And to be honest, I think logarithms are probably the hardest out of these last two, between logarithms and exponentials. Now, we're starting this with pre-cal review. Exponentials. Logarithms start low and swoop slow, right? Exponentials start around 0 and then swoop high. They grow really quickly. Doesn't matter what base they have. B is just a number. So we're talking about 2 to the x, or we're talking about 7 to the x, or we're talking about e to the x. They're all exponential functions. Variables are up top. They swoop up. And we learned that in our basic graphs. We have that in our basic graphs for e to the x specifically. We know we could talk about their domain, their range, yada, yada, yada. But let's talk about some calculus stuff, like what's the limit as x goes to infinity of any positive exponential function? Infinity. It's just going to go. And it's not just going to go. It's going to go really fast. It's going to be a high infinity. But yeah, it's infinity. A high infinity, or a great with a high magnitude. Infinity with a high magnitude. What happens as I go to negative infinity? 0. That's a common mistake of calculus kids. When you're looking at a graph, hopefully you can see it goes to 0, but when you're just looking at a function, it tends to get all jumbled. b to negative infinity, e to negative infinity, that's going to 0. And we already learned the basic rule of what's the derivative of e to the x? E was easy, right? And if I have a u, it would be e to the u times u prime. True? Couple more seconds. So how then are we going to find the derivative of b to the x? How then are we going to find the derivative of b to the x? Can we change a base of an exponential? No. We can only do that for logs. So actually, there is another facet to logarithmic differentiation that says something is stuck in a power. You have to get to them. We did this in pre-cal. What can we put in that lets the power come down? No derivative. ln's. Did we do that in pre-cal if we want someone to come down? Then I could just rewriting. I could bring the x down, no deriving. Now, this is actually a foreshadowing of something to come. Because right now your y's all messed up. He's in an ln. There's some process called implicit differentiation, blah, blah, blah. We'll see it next chapter, or I should say chapter 2, part B. But let me just show you what happens. Let me just show you what happens. We're actually allowed to take derivatives of pieces even with y's in them. And we would take it just with chain rule, and we would say, what's the derivative of ln of anything? 1 over, right? 1 over. 1 over who? 1 over y. Times, u prime. Who's u prime? Y prime. Just hang in there. We're going to spend a whole section on it after we finish this part of the chapter. The next piece. You would think maybe a product rule, but isn't ln of b just a constant? Times, we can just put the constant in front and keep them. Derivative of x is 1. Now, we're trying to find dy dx. We're trying to find y prime. So actually what we have to get y prime alone. We multiply the other side by y. And then we say, well, that doesn't look right. Who wants a derivative rule with y in it? Nobody. So who was y? So we plug in. Now, guys, you don't have to understand that entire process. I'm kind of foreshadowing something to come, but I'm showing you that actually using ln's, I can get down to who is the derivative of b to the x. B to the x, just like e, but b is not e, so we have to compensate just like we did with log base b. And we put an ln of b next to exponential base to the x times ln b. So that gets us up to, you got it okay? Don't have to have this page memorized, it's just more of an understanding like, huh, what? Oh, that looks kind of similar. Derivatives of exponential functions. We already wrote down e to the x. I know, but we haven't written down e to the u. What's the derivative of e to the x? Quick review. E to the x. So what would be the derivative of e to the u? Rewrite it. E to the u, but what else do you need? U prime. What's the derivative of b to the x? Well, he's exponential, so rewrite him. Exponential, always rewrite, times, oh, b is not an e, so we have to compensate, right? Ln of b. What changes if I have b to the u? B to the u, technically ln of b, just don't forget your u prime. Just don't forget your u prime. This is our final, praise the Lord, huh? Forever. If I can get my rectangle. I know e to the x We have him twice, but he really is that important. And I think by writing him, you remember, hey, exponential functions really behave the same. Exponential functions really behave the same. We do some practice and we have a couple minutes. Don't go back in. Forever number 15. Whew, we got there. How many rules are there really? Well, didn't we already? Shouldn't we know him? So really there's one new one, with x's and with u's. So really today you just saw 3 new formulas. ln, oh, we already kind of know him too. Never mind, we really just saw 2 new formulas. Log base b, what do we do with x or with u? And then b to the power of. What do we do with x or with u? Okay? Let's try to get a few examples in before we're done. Okay, we're going to do them all together. And you guys are going to practice hard in your homework. We have a 0 period tomorrow to keep practicing, keep asking, to keep working. The more you practice and the more you practice correctly, the more ingrained it will become and the easier it will become. 2 to the x. He's exponential. Rewrite him. Just like e to the x. We love these guys, except is 2e. No. So we compensate with an ln of b. Done. The rule says the derivative of b to the x is b to the x times ln b. Done. Now, hold on. He's one that we've done before. E to the u. I want you guys to try to solve them. Derivative of e to the u. Bridget.
Would it like tell you to use logarithms?
It's not going to tell you to put this in, because that's the rule that we're going to memorize really good. So remember, like power rule, how we memorize, bring down the power, subtract 1, and now it's like second nature? That's what these hopefully will become. Taking the derivative of anything to the x, any number to the x will be that number to the x times ln number. So that's one of those memorizing. Does that kind of make sense? I have an e to the u. What do? He's exponential. Rewrite him. Oh. Times ln. Oh, no, he's e. He's fine. Oh, but what do I need to multiply by? U prime. And to make it pretty, I would rewrite that 2x in front just so that there's no confusion. Remember, e to the, we love him. He stays the same, times u prime. And where did u prime come from? What's the derivative of who's inside? Derivative of x squared is 2x. Oh, look at that last one. What are we going to do to him? We kind of do it 2 ways. We could do quotient rule. Or we could rewrite and say, wait a minute, like bases? Couldn't we subtract the powers? E to the u times u prime. All right. Kiddos. Do we need to memorize those rules? Oh, yes. We do. Study your forevers. Homework, remember, it's the shorter second half of 2-4. Do the best you can. We have 0 period. We can work together on it if you get stuck tonight. But you must study forever. Bye, guys.
The forever quiz on all the time is 6 to 15.
6 through 15 is normal credit. Extra credit could come through 1 through 5 or hard credit.